Welcome back. Let's continue the discussion on transport PDM model. So, what we have looked at the basic definitions and then the governing equations in the Eulerian framework, and then we have also discussed about some of the unclosed terms which are sitting there in the transport equation and how to close them. That is what we are now doing it. Now, in order to do that, we have also discussed the different velocity PDF, velocity scalar PDF and also the scalar PDF, and then we started looking at the governing equation. This is what we are up to. So, once you look at those things in the Fabry averaged equation system, so you get three unclosed terms, number 1, 2 and 3. This is Reynolds stress, turbulent scalar flux, mean source term. Now, when you close them, previously we have already seen that to close that this term we use some turbulence model. So, here also if you are only using scalar PDF approach, then use the turbulence model or any Rans model to close it. Scalar flux we can use the gradient diffusion model, and the only reaction source term we can close it using the scalar PDF information. So, then all the terms sitting here, the unclosed term, they become closed, or alternatively one can make it slightly more accurate in the sense in the description and close this term using velocity scalar PDF. So, now this Reynolds stress component, instead of closing from the Rans equation, use the information of the velocity PDF, one can close this. And similarly, turbulent scalar flux, one use both the velocity scalar joint PDF and close it, and the source term using scalar PDF. So, this will make things now closed in the governing equations, and the solution obviously, as we said, because of the dimensionality, one has to adopt from some Monte Carlo based technique. Now, we look at consider the mass density function. So, instead of probability to have certain values of scalar, we say probability to have a certain amount of mass with certain value of scalar. So, which will lead to this new definition, which is the scalar mass density function. So, this is defined as f phi psi xt is a rho psi, and this is the scalar PDF, which will be mean rho and the Fabry average f phi psi dt. So, this is our scalar mass density PDF or mass density function. Now, properties of this composition mass density function. So, one can look at the different properties, like our mass density function is defined like this, rho over f phi on psi and t. So, if we integrate this over d psi, this will get me this is my mean density, and the normalization criteria also give me 1. So, what important here, this particular property, which is if f phi is q psi and d psi, then one can write this is the variable that mean density and q. This decomposition would help to simplify some of the situation. Now, we will look at our transport equation for the scalar PDF. So, it is nothing but an equation PDF of a set of independent scalar variable which is derived, modeled and solved. When we say it is derived, then there would be some unclosed term. So, because of this unclosed term, we can model this, and then finally, so we can see this unclosed equation of the mass density function. This will be written as del f phi by del t, this is the convection, this is one term which is in terms of chemical source term, right hand side this is a turbulent flux, and then this is the mixing term or the scalar flux term. Here one of the advantage of this equation is that chemical source term is in closed form. This is one of the biggest advantage. Typically when you do the Fabry averaging or density weighted averaging, our chemical source term in the mass transfer equation become unclosed. So that gives or brings lot of challenges to close that term, and that is why we started discussing the simple reaction models or combustion models, how to close that term. However, having this chemical source term in closed form, we still have other two term on the right hand side, this term 1 and 2, this is the turbulent flux term and the micro mixing term, they are unclosed. So one needs some sort of enclosure for these two particular terms to be closed, where theta alpha is the diffusion flux which is depend as a regular ways. Now one see this, one way to look at this conditional mean, that means this term fluctuation of u which is conditioned on psi, it would be equated with mean of u for all events where psi equals to phi is true. That means it is a very simple way to close that particular term which contain that velocity fluctuation. So that allows that you consider the mean of fluctuations for all the events where you have psi equals to phi which is true. Now this term that becomes unclosed because your velocity statistics are not available in scalar PDF framework. So they are only the distribution of the scalar quantities which are available, so no information which is available for the velocity statistics. That is why we have to use some expression to close that term. Now the other term theta alpha which is conditioned on psi, which is mean of theta alpha for all events where theta psi is true. This is also unclosed because statistics of quantities which are containing the spatial derivative are not available in one point scalar PDF framework. So since some information which are not available, that require this closure of this term. Now one can look at this particular process. This is our function, and this is in the variable space psi. Now the process which influencing the scalar PDF, now we can look at the, this is a transport in physical space. So this is at a particular time t, and this is at t plus delta t. So what happens, this scalar PDF which is a quantity which would be again convected by the mean velocity. So here if it is at x plus delta s, and this would be at this position. Similarly, the diffusion by turbulent velocity fluctuation. So this is the at position x, due to the diffusion of the fluctuation it will be like this, and similarly at t plus delta t this could be the shape, and due to diffusion this could be like this. So that means one hand there is an effect of the convection, secondly there is an effect of these things. Now then similarly micro mixing term. So here is position x, then t plus delta t, because of micro mixing, so it takes a different shape. Similarly due to reaction at next time level this becomes like this. So reaction which will essentially lead to the consumption or destruction of some consumption or production of some of the species, and that will be like that. Now we can look at the closure form of the scalar PDF equation. So the we are looking at the terms which are on the right hand side. These are the terms that we talk about, this right hand side term, and the is a one term which is transformed by the turbulent velocity fluctuation. So, we use the gradient diffusion assumption and we write this term which is unclosed. This is an unclosed term. It is closed like using like an gamma t del del xi of f phi by rho, where this is nothing but mu t by sigma t. Sigma t is turbulent Smith number and this is turbulent viscosity. Now, this is an simplest assumption or very common assumption one can use, this gradient diffusion assumption, but for some flows this may fail. Now, accurate enough for complex flow field, but this will fail if there is a counter gradient diffusion occurs. So, this is a, but most of the wide range of cases this works nicely, but certain cases this actually fails where the counter gradient actually takes place. Now, this term is closed when we take joint velocity scalar PDF, but since the velocity statistics is not available from the scalar PDF information, that is why we have to close it, and the simple way to close it is this. Now, the second term on the right hand side which requires closure is this term, the fluctuating of this term. There also you use the gradient assumption, also we use this is the turbulent flux term, so we actually close it by the simple mean. Now, the term which is there, another term is the theta alpha which is 1 by rho, this is an micro mixing term. How do we do that? So, we use some micro mixing model. So, this is an interaction by exchange and mean, this is one kind of micro mixing models, and more details can be found in some of the review literature, and also there is a book by Rodney Fox where all these micro mixing terms and all these are discussed in details. So, this is an called interaction by exchange with the mean, IEM model, which is a very common and well known model. Now, when we look at this gradient term which remained unclosed in the PDF transport equation, now we close it by 2 into C phi omega and the gradient of del psi alpha with respect to this, where omega is the turbulent mixing frequency and C phi is the model constant which is a time scale ratio. Typical value which is often used is 2. So, for wide range of flows this works fine, but obviously having said that it also needs some tuning when there is a change in time scale. That means, if some flows which are kinetically controlled, that time one has to tweak this parameter a bit to take into account that thing, that the kinetically controlled situation. But another point one has to note here is that this IM model does not describe the change of shape of the PDF correctly, but this is simple enough to essentially close this mixing term. Now, we can look at the solution procedure of the PDF transport equation, and as we have already discussed, the most efficient method would be particle based method, the Monte Carlo solution. That means you need Lagrangian framework to solve it, because the dimensionality of the transport equation or the probability density function transport equation is so high, one cannot solve in regular method like your numerical methods like finite difference or finite volume kind of approach. So, it requires some special treatment, and the special treatment is like that it is solved in particle based method or in the Lagrangian framework, which is often known as Monte Carlo simulation, and this is proposed by Stephen Pope. So, the mass density function is represented by an ensemble particles. That means, if you look at this is your computational grid. So, each cell there will be large number of particles, and obviously these are not massless particles, and they will represent the mean properties of this particular cell. And if you look at the distribution in the composition phase, this is the mass density function distribution. So, mean fields are calculated from the particle properties obviously, and then when the equation of motion of particle properties are satisfied, it corresponding to a closure of the PDF equation. Now, the process which influence the fluid particles, there would be convection, like convection due to mean velocity. So, let us say if the particles are here at this position, at the next time step, because of this convection effect or the convection effect of the mean velocity, particles actually reach here. Okay. So, that is like you have some particles like you can think about your fluid particles which are always convected downstream due to convection. Secondly, there could be diffusion by turbulent velocity fluctuation. That means, let us say particles are here in the next spatial coordinate system, or if they are here and they goes to x plus dx, because of this diffusion they come here. Similarly, the particle by the time next time step, if they come here and then the diffusion also impact, then there could be mixing. So, because of the mixing you can see how they behave, and then finally reaction, which will allow to take into consideration of the scalars, the reactive scalars, which are either getting produced or consumed during this process. Now, how do we model these particle properties or the change of particle properties? Because we have already said that each computation cell will have some number of number of notional particles, and these particles do have some mass. These are not massless particle, and the particles collectively in a particular cell will determine the macroscopic property of that particular computational cell. So, these are very essential properties. So, as we said, the particles are having some mass, they also at a position x, and the scalar which is carried by these particles are phi star. Now, change of position in time step dt. So, from one position, so there will be delta x change for a particular particle. So, this is due to mean flow field and the gradient plus the other part and the Wiener process. So, this is an random process which will allow the particles to move stochastically. So, this Wiener process is known as an stochastic process. We allow these particles to move randomly within that particular cell, but the combined effect we can see what would be the displacement of these particles over a time step of dt. Now, similarly, there will be change of composition in time step of dt, and that also we can see if this is d phi alpha star, this is the phi alpha dt that is coming from the micro mixing model, and this is due to the source term of the chemical source term, which allows the particle to, that means there are two components, one is mixing, one is reaction, and the reactions are going to say how much is consumed or produced and something like that. So, the mixing model is closed like this using the IM model, which we have already discussed, and then this is the source term, chemical source term, which will also tells you how much there would be change in composition because of this time step change. Now, we can see the micromixing model behavior, how that actually behaves. So this is, you can think about, in this direction there is a one scalar which is in this direction, there is another scalar, and this is all the particles, and let us say the mean properties would be somewhere else, then the tendency of this each particle is to go towards the mean, and that is why we call it IEM, interchange by exchange and mean. So this is how the, in a mixing phenomena, or in the context of the mixing phenomena, you can think about this is going to be the particle behavior. So they always, though they are random, or their position is going to be determined randomly through this Wiener process and all these things, and also the effect of mean and the other fluctuations, but still in the mixing level they have a tendency to go towards the mean. So this is how IEM model actually captures this particle phenomenon. So if we somehow put up together the process of this transport scalar PDF, then we can see this is an sort of an hybrid approach. That means you have both Eulerian submodels and you have both Lagrangian submodels also. The reason is your PDF distribution function or the PDF transport equation cannot be solved completely in Eulerian framework, and the preferred or most preferred or most efficient solution algorithm is the Monte Carlo algorithm, which is the particle based Lagrangian algorithm. So which essentially makes this particular approach to be an hybrid approach. So what you have in your Eulerian submodel, if you look at it, so you have some finite Wheeler method to solve for mean fields, which will solve mean velocity, mean pressure, turbulent kinetic energy, dissipation rate, and you can determine the turbulent frequency from here, which is essentially epsilon by k. Now this is solved in your Eulerian framework, and this particular set of information you send it back to the Lagrangian framework or Lagrangian submodel. At the Lagrangian submodel, you look at individual particles. What you look at? You look at their position. So due to this randomness and the top of that, the effect, combined effect of the mean fields and the randomness, how their position changes, and also the change in the composition. This is the two things which is very important, that will, and then this change of composition is obviously impacted by reaction and micromixing. So these are also important submodel in the Lagrangian framework. So once we do that, then the particles randomly move from this place to that place, and so, but still there would be collection of particles which sit or stay inside the one particular cell or computational cell. But another thing here to be note there, once the particles or the number of particles which stay inside the computational cell or Eulerian cell, so that's where you find out the macroscopic property like density, which is again sent back here, and this is where, and also one has to make sure that the global mass conservation is not violated. That means any Eulerian cell which will have the corresponding particle cell particles there, so the mass conservation, so this is the sum of the total particle mass should be same with this. This is one thing, there is a checking which is constantly done to have an proper handshaking between these two framework. And then also one has to account for, let us say you start by assuming okay n number of particles in each computational or Eulerian grid, then due to this fluctuation, randomness of the motion, position, the particle may cross the cell boundary. So if that happens, you have to immediately account for that information. So these particles move to the other cell, where there would be n plus 1 number of particles, but then through the mass conservation or global mass conservation you redistribute the mass amongst those particles into n number of particles. Similarly, when there is a loss of particle from a particular cell, then again you look at the global mass conservation. From there you redistribute the mass to the n number of particles. So, these are the things one has to take into account while there is a information transfer between these two sum models and the solution process or progress in this fashion. But when you have these hybrid kind of models, still it requires lot of memory. The reason is the following: you have Eulerian cells which could be of order of few thousand million cells depending on the problem, but now each Eulerian cell will have n number of particles. Then your number of particles that you are dealing with, that x number of Eulerian cell into n particles. So, that many particles you are in totality dealing with. So, that is the still memory requirement is high. Then since the solution is going back and forth between these two sum models, Eulerian and Lagrangian framework, it is slow, but when you pay the price in this sense, it is quite accurate and give you, because this captures the randomness of the motion. This is an example which is picked up from an transported PDF calculation where the local extension was predicted. So, this is using natural gas. So, if we put the points together for the scalar PDF discussion, so the combination with the RANS model for velocity, numerically robust and convenient for use in combination with existing CFD code like finite volume method. So, this is how we combine with the RANS framework. That is one of the advantage. Then the second advantage is that chemical source term appears in closed form. This is very important, because this is one of the term which creates lot of problem along with challenges to close it in a governing equation, because that is quite steep and make the system of equation to be quite steep enough for solution. Then closure and solution of PDF transport equation are mostly done in the framework of particle method, or rather I would say it is an hybrid approach which is adapted. So, this has both Eulerian and Lagrangian. So, the combination of these two give you the best solution method, and then we use random walk model. This is for position or random position or rather distribution of particles. So, this particular model will allow to estimate the random distribution of the particles, and micromixing model to close the unclosed term in the mixing phenomena. So, this is what one can see how we get the solution of a scalar PDF transport equation. So, we will stop here and continue this discussion further. Now, we look at the velocity scalar PDF and we look at how one can obtain the solution and what are the issues and how to close those particle positions and their mixing in the next lecture. Thank you.